Your audio is fine, and we are recording.
Outstanding. Well, Jeff, thank you very much. It's my pleasure to be here for tonight's Hiller Hangar talk. When we were looking for a potential mid-February topic, we looked at a couple of different ideas and kept coming back to the idea of really taking a look at what's going on in the solar system this week and this month, because there are some very exciting things going on. For those of you who may be watching the news, we have a new spacecraft approaching Mars right now. That's going to be the Perseverance rover carrying the Ingenuity helicopter, and it's going to be arriving at Mars tomorrow. So Mars will be in the news one way or the other. We're either going to have a fabulous news story about a successful landing on Mars, or we're going to have a big ticket headline about a terrible Mars failure on Mars. So one way or the other, Mars is going to be in the news tomorrow. This is a great opportunity for us to take a look a little bit at Mars and how what's happening in our solar system right now kind of connects not only to our exploration of the solar system, but also even to our collection here inside the Hiller Aviation Museum, because there are some really neat things to connect. Now, I could just go on and have you look at my lovely face and the background behind me all the way through, but I think it'll be more fun if I share some slides with you. So let's see if technology works for us today. All right, I see my first slide. Okay, that's usually a good sign. Well, Red Planet Robots is the name of our talk tonight. There has been the dream of exploring Mars for a really long time, and a big part of that dream is for people to actually go there physically and explore it. That hasn't happened to date, but there have been about 50 different robots that have been sent out, and in a very real way, we have been exploring Mars for about 60 years now through these robotic emissaries that we've been sending, and sometimes succeeding in sending all the way out to the next planet in our solar system, Mars. So Red Planet Robots is a nice way of tying this together and really helping us gain some insights into how the exploration of Mars has gone down. So what I'm going to try to do in this talk, if everything works smoothly, is just kind of give you an idea about Mars and its place in our culture and history very briefly, the early efforts to understand it, mostly from here on Earth, and then the history of robotic exploration, starting back in the 1960s, all the way through tomorrow afternoon, when hopefully we will be getting word back that a new robot has safely landed on the surface, or as I said, has created a brand new Martian crater, one way or the other. Well, today we know a lot more about Mars than was the case even 50 years ago, even 25 years ago. Our knowledge of this planet is always evolving. And one of the things that has always been compelling about Mars is the place it holds in our imagination, even before telescopes. Out of all the planets visible to the naked eye, Mars is unique in that it goes through a tremendous range in brightness. It has a very unique apparent motion through the sky as it goes around our sun. And its color, its very distinct reddish color as it waxes and wanes in brightness through time. So even before there were any telescopes, folks thought Mars was kind of odd, kind of unusual, kind of peculiar. As we developed better technology, it became possible for us to get an up-close look. But due to its very nature as a planet, Mars has been one of the most elusive planets in our solar system for us to learn about. So Percival Lowell, you probably never heard of him, but you are probably familiar with some of the things that he did. He was not the first astronomer to use a telescope to study Mars, but he was one of the ones who was perhaps most responsible for pushing Mars forward in our modern day imaginations. Telescopes had been around since the early 17th century. Galileo Galilei made a very simple optical tube with some lenses in it, and he was able to very, very quickly, over just a couple of months in couple of weeks actually, in January 1610, make some spectacular discoveries about Venus, about Jupiter, about our Milky Way. Mars, though, was always elusive for him. His optics just weren't good enough. And one of the reasons for this is Mars is very small, and it's in an orbit that sometimes carries it quite close to the Earth, at least by solar system standards, but other times carries it quite far away. Galileo was able to look at Jupiter. Jupiter is a big place. It's farther away from Earth than Mars is. So we're about 100 million miles away from the sun. Not quite that far, but pretty close. Jupiter is about 500 million miles, so about 500 million miles out. So that's a big distance by solar system standards, but it's also a really big planet. It's 10 times the diameter of the Earth, and it's got these huge moons whirling around it. There's all kinds of stuff. Even with a crummy 1610 telescope, Galileo was able to determine some cool things about Jupiter and some of the other large planets in the solar system as well. Mars is very small. It's about half the diameter of Earth. And its orbit sometimes carries it not quite as far away as Jupiter, but a lot farther proportionately than Mars is when it's close to Earth. So it's very difficult to study. Also, I will say that when Lowell was doing his observations, which was not in the 1600s, but actually in the late 19th century, 1890s in particular, he was using a lensed telescope, what we would call a refractor telescope, which we never really got any better than we were in the late 19th century when it came to refracting telescopes. So telescopes in general, they got a lot better after the 1890s, but the kinds of telescopes that astronomers and engineers would build in the 20th century, like the ones that Hubble, for instance, might use to find out more about galaxies and the expansion of the universe, they were great for looking at things very far away in space, much farther away than objects in our solar system, but they weren't that great for looking at planets. The telescopes that work best for looking at planets are the ones with lenses. And after about the 1890s, folks realized, it's really pointless trying to make a bigger telescope with a lens because there are physical constraints that make it very difficult to do. One of the most beautiful refracting telescopes I've ever had the opportunity to see, you have an opportunity to see as well. It's the 36-inch refracting telescope at Lick Observatory, just east of San Jose. It's not generally used for observations anymore. That technology is obsolete. However, it is a great example of a refracting telescope that would be very suitable for observing planets. Lowell was using very similar technology with his telescopes. He built his own observatory near Flagstaff, Arizona. It's called Mars Hill. That's also today called Lowell Observatory. But from that location, Lowell was able to observe the planets, and he was particularly interested in Mars. But one of the things that characterized late 19th century telescopic observations, the only instrument that was really involved besides the telescope was the astronomer's eye. And the data recording process was for the astronomer to draw a sketch. And compared to today, when nearly all data is collected through long duration photos, or especially spectrometry, looking at the different colors coming from the stars or the amount of light coming across a different image, the idea of sitting at the telescope and looking through the lens and trying to draw what you're seeing as a scientific research project, it is a little bit open to interpretation. And most famously, Lowell seized on a report from an Italian astronomer by the name of Schiaparelli, who had reported canali, which in Italian means channels, on the surface of Mars. Well, somewhere along the line, literally, that was lost in translation, and that became popularized not as channels in English, but as canals. Now, a channel can be a naturally occurring feature. A canal is by definition artificially created. So from this idea that there are these strange features on Mars that might be these channels that I can glimpse through my telescope, suddenly this whole narrative arose of a civilization on Mars that was building canals. The technology that was available back in the late 19th century did let us see certain things about Mars. There wasn't a whole lot of atmosphere. It looked like it was a pretty cold place. Hard to see any place that would be a large ocean. There were some dark areas that kind of got larger and smaller over the seasons, but it didn't look like there was a whole lot of, it's certainly not a worldwide ocean the way we have here on Earth. Lowell really seized on this, and he would do many drawings and he would publish many drawings. The drawing I have here was a drawing from a newspaper in 1898. Here's the latest map of Mars, and it shows these lines all over the place. The lines don't exist. But even as late as 1960, the dawn of space exploration, scientists weren't sure if they existed or not, simply because the technology to observe Mars from Earth didn't get a whole lot better than what Lowell had available in the late 19th century. That did all change, however, but not before Mars had seized a place in our imagination. In the late 19th and early 20th century, there was an explosion of popular literature. I guess today it would be a Netflix show. Back then, it was a bunch of books, and there were magazines that would put out serialized stories about things happening on Mars. Usually, it would take the form of something along the lines of H.G. Wells's War of the Worlds. There are these hostile Martians that are going to invade Earth, or perhaps like the John Burroughs stories, exploring Mars and going to Mars and trying to find out where this ancient civilization may have gone to. But this was all happening absent very much real data about what was happening on the surface of Mars. So up until about 1960, even with the best telescopes that we have at Lick Observatory or Yerkes Observatory or Lowell Observatory, we really had hit our limit in terms of what we were able to learn about the fourth planet in our solar system. And that really primed the pump for the spacecraft exploration to follow. Mariner 4 is a spacecraft that very few folks these days have heard of, but back in 1964, it was a really big deal. Why was it a really big deal? It was the first robot to fly. It was the first robot to successfully fly to Mars. You notice it's not Mariner 1. Now, in fairness, Mariner 1 was a robot, and it didn't go to Mars at all. It was aimed at Venus. Didn't make it to Venus, it failed. Mariner 2 went to Venus. The first spacecraft launched towards Mars from the United States was Mariner 3. Didn't make it. Back in the early days of space exploration, we sent robots to a lot of different places, and they didn't always make it. And at that point, NASA took the attitude kind of similar to like the Spanish during the Great Period of Exploration or the Portuguese. We're not just going to send the Santa Maria to the New World with Columbus. We're going to send the Nina, Pinta, and Santa Maria because who knows if they're all going to make it or not. When the first circumnavigation around the world was made, it was a fleet of 5 ships that was sent, and only 1 made it. Well, back in the 1960s, if you're relying on rocket technology to get you someplace, you better be prepared for failure. Mariner 3 was launched a few weeks before Mariner 4 was scheduled to go, and its launch vehicle failed. The top of the rocket didn't pop off properly. But, you know, there was a spare. It was ready to go. They redesigned the nose cone of the rocket, and they sent it off to Mars. And it did arrive about 9 months later. Now, one thing that comes up frequently in Mars exploration is this idea of only being able to go at certain times. Unless you have the largest rocket you could possibly imagine, it's really only possible to go to Mars from Earth for a few weeks every 2 years. The planets are just not lined up properly to make that a feasible trip for the rest of the time. So about every 2 years, a little bit longer than that, but roughly every 2 years, Mars and Earth line up, and there's an opportunity to launch a reasonably sized rocket with a reasonably sized robot or whatever other cargo you want to send out across the solar system in and on, and launch it towards Mars. And it's going to get there somewhere between 6 and 9 months later on. Most of the ones we've been sending lately have been on a 7 or 8 month trajectory. All right. So Mariner 4 was launched, and 7 or 8 months later, it made it to Mars. Didn't stop. Technology back then was very limited. It had the ability to fly by Mars once and keep on going. It's not going to land. It's not even going to slow down and orbit Mars. It just blew past. It took 22 really crummy TV quality pictures, and this is 1960s TV quality pictures, and over a period of several days, slowly transmitted the data back to Earth. And we saw our first close-up pictures of Mars. I've got one of the Mariner 4 pictures right there. It looks like the surface of the moon. This is really discouraging for a lot of folks, including the scientists. We had traveled across tens of millions of miles of space. Actually, the trajectory is more like hundreds of millions of miles of space. Made it to Mars, finally got a good look at the surface, and there's craters. If we wanted craters, we could have gone a tiny fraction of the distance to the moon. There's plenty of craters there. Now, as the scientists looked at these 22 pictures more closely, they did see some things that were intriguing. Among other things, there were signs of weathering on these craters. There weren't as many craters as they might have expected, but nonetheless, we're looking at craters. And that's one of the drawbacks with this method of space exploration. The robot gets to the planet, blows past, keeps on going. It's the easiest thing to do. You need the smallest robot and the smallest rocket, but the amount of data you collect is very limited. As it happened, the 22 little pictures that Mariner 4 was able to send back from Mars happened to be of some of the least interesting terrain on the planet. There is a reflight of the mission, Mariner 6 and 7, for one of the few times both robots successfully made their trip, and Mariner 6 and 7 both flew past Mars in 1969, just a few weeks after humans landed on the moon, so there wasn't a whole lot of attention. And even though these were somewhat more sophisticated robots, they did the same thing. They flew by Mars and kept on going. They took more pictures, they took better pictures, but also luck was against them, and they took pictures of kind of the more tedious terrain. We needed to do something different. We needed to increase our ability to collect data at Mars. And there are 2 ways that scientists wanted to go about this. First, they wanted to be able to take a robot similar to a Mariner 4 or a Mariner 6 or 7 and slow it down at Mars so that it could actually go into orbit and collect data over a much longer time and look at more of the planet. Heck, why not take pictures of the whole planet, not just a few little postage stamp pictures as we go flying by? You can do that if you slow down and go into orbit. You can stay there for months and not just hours. The second thing, and this is even more challenging, is to go to Mars and land on the surface. And in 1971, attempts were made to do both. All right. 1971 was a particularly favorable opportunity to go to Mars. One of the many peculiar things about Mars is, unlike the other inner planets, except maybe Mercury, it has a more elliptical orbit than most. Unless you get way out in the solar system to the dwarf planets like Pluto, it's hard to find planets out in our solar system that have a more eccentric orbit than Mars. It does come close to Earth, relatively close to Earth, every couple of years. But because of the eccentricity in Mars's orbit, there can be a 20 or 30 million mile difference in how close it gets at different, what we call oppositions. 1965, it was kind of okay. 1969, it wasn't too bad. 1971 was especially auspicious. And it was possible, because Mars was a little bit closer to Earth that time around, to send a bigger robot. So NASA decided to try the same sort of thing they had been doing with Mariner 4, 6, and 7, but to make it bigger, give it an engine, give it a bunch of fuel, and have it slow down when it got to Mars and orbit the red planet. Now, at the same time, on the other side of the world, the Soviet Union had a very ambitious space program as well. In fact, they had been sending robots towards Mars since 1960, but their luck doing so was even worse than what the United States has experienced. Every probe they launched in the 1960s failed. But because the alignment of the planets was more favorable in 1971, they figured, hey, this is our opportunity. We're going to send really big robots. And this time we're actually going to tell people that we're sending them. So instead of having a generic Cosmos designation, which the Soviet Union frequently did with rockets and spacecraft, they didn't really want to share with anyone what they were supposed to do. Mars 1 and Mars 2 got names after they left Earth orbit, and they departed during the 1971 launch opportunity. Likewise, NASA launched 2 spacecraft built at JPL, Mariner 8 and Mariner 9. Mariner 8, I keep waiting for somebody to find it because it's at the bottom of the Atlantic Ocean. It didn't make it even to orbit this time. Oh. Fortunately, the rocket worked for Mariner 9. Yeah, it happens a lot. It happens a lot. Mariner 9 did, however, successfully leave Earth orbit, reach Mars, and it was able to fire a rocket motor once it got there and go into orbit around Mars. And the first images that came back from Mariner 9 were a little bit different than anything we had seen before. These aren't the first images, but they're characteristic of them. The Mars picture, and it is actually a Mars picture that I've got on the lower right there, that's Mariner 9 data from shortly after it arrived at Mars. The entire planet was covered in a planet-wide dust storm. Right away, scientists were intrigued. I mean, hey, we were saying there's craters, so it's like the moon. But wait, the moon doesn't have any weather at all. It's dead. You mean there's not just a dust storm at Mars, but a dust storm that can cover the entire planet in dust? Whoa, that's amazing. They distributed their information and settled down to wait for the dust to settle out. And since they were going in orbit, they weren't just blowing by, they had time to spare. The Soviets, however, boy, talk about bad luck. Mariner 9 actually got to Mars first, shortly before Mars 1 and Mars 2 arrived at Mars. So the Soviet Space Agency knew what was coming up. They were going to try to land in the teeth of a 200-mile-an-hour dust storm. The robots that the Soviet Union sent to Mars in 1971 were sophisticated by 1970s standards, but not by modern standards or even by late 1970s standards. They had no ability to change course. They had no ability to wait. I'm not even sure it was technically possible for them to wait. I know the way that JPL has been sending spacecraft to Mars recently, they also would not have the opportunity to wait. So they had no choice but to try to land on Mars anyway. The picture I've got on the upper left is Mars 2. That's actually an engineering mock-up that Roscosmos put out. It's same size, same shape. It used a parachute and then made a hard landing on the surface. And I've got to hand it to them. Even with the dust storm going on, we don't know what happened to Mars 1. Mars 2 landed on the surface and returned data for 40 seconds. That's it. It might have blown over after it landed. It might have had some kind of failure because of the weather. It might have had a failure unrelated to the weather. A lot of bad things can happen when you get to the surface of Mars. Regardless, no meaningful science data was returned. So the whole business of landing on the surface, that was going to have to wait a little while longer. On the other hand, Mariner 9, after a few weeks, observed the Martian surface as the dust storm began to abate. And what it was able to discover fundamentally changed our understanding of Mars for the first of many times. So today we have a much better idea of what Mars is like, and the beginning of that understanding comes from Mariner 9 by doing a long-term, and in the case of Mariner 9, long-term was about 3 months, study of the entire planet. It was possible to see not just little parts of it, but all of it. It was able to discover what we see here, the Tharsis Montes, Olympus Mons in the lower left of the image, the largest volcano in the solar system. It's about 10 miles high. It's the size of the state of Arizona. Arcea, Ascreas, and Pavanis Mons over off to the east. Those each are the size of a US state. They're enormous volcanoes. They're essentially sticking out of the atmosphere. The calderas of these mountains were the first things that Mariner 9 was able to detect as the dust slowly settled. A little bit farther to the east is Valles Marineris. It's a gigantic canyon. It would stretch coast to coast in the United States. It's miles deep, much larger than the Grand Canyon. And perhaps most intriguingly, as Mariner 9 collected more data, it was able to detect features on the surface of Mars that looked very suggestive of liquid water having been on the surface in the past. Right now, Mars, I mean, you can kind of see it here. There's no water down there. It's dry. There's a very small amount of moisture in the atmosphere, but even by atmosphere standards, it's very, very trace amounts. But there are unmistakable signs of what looks like the past history of liquid water running on its surface. How can that inform our understanding of what Mars was like in the past and what might have been possible on Mars in the past? Well, things hadn't changed by the early 1970s. The true quest was still to land safely on Mars. And so in 1975, the United States launched 2 more spacecraft. And again, amazingly, they both worked this time, Viking 1 and Viking 2. And during the summer and fall of 1976, they arrived at Mars and successfully landed on the planet. This is Viking 1. It landed in Chrysae Planitia, the first place on Mars to have a working robot. It actually lasted for about 6 years. It was able to take pictures of the surface. It was able to return weather data. I'm not sure if it was Viking 1 or Viking 2, but one of them was able to return a little bit of seismic data. It didn't work as well as they had perhaps hoped because the spacecraft kept contaminating the data, but nonetheless, it worked. It landed. And it really changed our understanding of Mars. There was even a very ambitious effort to try to detect microbial life on Mars with this mission. This is back in 1976. And the life detection experiment involved a robotic arm scooping up some soil and putting it in a little lab inside each spacecraft. And the results ended up being completely inconclusive because the experiments that had been developed on Earth gave results on Mars that were just crazy. And they were crazy because the scientists on Earth had not truly appreciated how alien the chemistry of the Martian soil would be. So experiments that on Earth would have been very effective in detecting life on Mars just detected very strange soil chemistry. And it was ambiguous one way or the other what would happen. Well, this is sort of the first chapter of Mars exploration with robots from the 1960s through 1976. So the natural question is, what came next? How can you follow these fabulous discoveries of volcanoes, of canyons, of polar ice caps that change with the seasons, of these discoveries on the surface? And the answer is nothing. We stopped exploring Mars. We, being the United States, we stopped exploring Mars because we found other things to explore and or, this is kind of expensive. Viking was kind of expensive. Let's not do this for a while. The Soviet Union gave up in disgust after Mars 1 and Mars 2. They went on to Venus and ended up being far more successful exploring the second planet than they had been exploring the fourth planet. But for a long time, there were no robotic missions sent from Earth to Mars. Finally, in the early 1990s, a spacecraft called Mars Observer was launched to the red planet. It departed in 1992 and arrived in 1993. I remember I was newly graduated with my astrophysics degree. I was working at a planetarium in Chicago at the time. I was delighted that this was going to happen. It was the first time since I was a little kid that anybody was sending a robot to Mars. And in some ways, unfortunately, the entire scientific community had the same attitude. So, wow, we have a chance to go to Mars. We haven't gone to Mars in almost 20 years. And as a result, even though Mars Observer was never intended to land on the surface, it slowly accumulated more and more scientific instruments as each different discipline in science and astrogeology, I should say, wanted to put an instrument, some kind of sensor on this spacecraft. A NASA administrator a few years later would characterize it as building Battlestar Galactica to go to Mars. It was kind of neat to have such a capable spacecraft, but there's an enormous weakness with this approach, and it became obvious as Mars Observer arrived at Mars. This picture was taken about 3 days before Mars Observer arrived at Mars in 1993. It is the best data of Mars it ever returned, because when it attempted to go into Martian orbit, there was a problem with the fuel system, and best we can determine from the data that was collected, it exploded. Boy, that's a bummer. That's just no fun. But it happens at Mars a lot. And again, one of the weaknesses of this approach of cramming every instrument you can imagine, every tool you can possibly want onto one spaceship, is if it doesn't work, well, then you've got a lot of hardware on the bottom of the ocean or in orbit around Mars or in a crater on the Martian surface, and you don't have any plan B. Well, I will say that this disaster, nobody got hurt except for a lot of people's feelings, but this disaster really did pave the way for the renaissance that we have today in Martian exploration, because it gave rise to what today we call the Mars Exploration Program. We have known since Mariner 9 that there are water-related features on Mars. And we've been sending robots to explore Mars from the United States since 1964, but there was never really this kind of theme or framework in which we would send robots out to Mars. The Mars Exploration Program, which came immediately following the Mars Observer failure, kind of did two things that were very, very helpful. First of all, it created a mission statement for the exploration of Mars. And with one or two exceptions, pretty much every Mars mission that's been sent since the early 1990s has fallen into this framework. And the main idea, there are four main themes, but the biggest one is to understand what has happened to water on the surface of Mars. What's the history of water? Because by understanding water and where it was in the past and where it is now and what's going to happen to it in the future, we will be able to deduce whether or not there's the potential for life to have ever survived on the surface of Mars, either in the past or in the present. And it also informs some of our choices about putting life on Mars in the form of astronaut crews in the future. So this whole follow the water idea has created a very structured way in which we can continue to explore the red planet. The second thing that came out of the development of the Mars Exploration Program, especially for the first 1 or 2 decades, is instead of putting 1 or 2 spaceships out towards Mars and cramming as many instruments as possible onto them, hey, let's make smaller robots. Let's send them for the first couple of decades every 2 years. Every time Earth and Mars line up, let's send another robot. But let's have it be smaller so it's not so expensive. Let's have it only have a few instruments on it instead of everybody's instrument. Everybody and their nephew gets an instrument on the next Mars mission. No, no, no. We'll just do a few at a time. And that way, it's not as expensive up front. That way, we have multiple spacecraft at Mars that can support each other. And if one of them fails, it's not like everything's gone out in tubes for the next 20 years. And that's proven to be a much more sustainable strategy. And that strategy began to be put into effect in 1996. Well, 1996 is when the modern exploration of Mars really began. On Independence Day of that year, the Mars Pathfinder mission landed on Mars. And from that moment on, there has been at least one robotic spacecraft continuously in operation at or around Mars. I say at least one. Right now, there's 9, which is really mind-blowing to me. Tomorrow, there's going to hopefully be 10. Maybe there'll still be 9. We're not quite sure. But regardless, there has been a robust assortment of robotic spacecraft on Mars or around Mars. Pathfinder was really neat. I remember being in a conference room in Pasadena when Pathfinder landed, and the pictures came out within an hour or two, which was a revelation, and we could see this cool landscape. Pathfinder technically was not part of the Mars Exploration Program. It belonged to the Discovery Program and was mostly an engineering exercise, but the data it sent back exceeded everybody's expectations. One of the really cool things that was tested on the Pathfinder mission was this business of, hey, let's try a little mobile vehicle that can move around and look at different rocks and go right up to them and touch them and collect data from them. That was the Sojourner rover. It's in the inset picture at the lower right. And it worked. It worked great. And the Pathfinder mission was very, very exciting. But in some ways, more fundamentally revealing of Mars was the next robot that arrived a few months later. In November of that year, the Mars Global Surveyor. And I've got a little picture of it in the upper right. That one didn't get all the good press. It was just an orbiter. It didn't land. It didn't have a 4th of July party associated with it. But the data it sent back fundamentally changed our understanding of Mars yet again. One of the reasons for that is it collected a tremendous amount of data beyond visual imagery, more than just pictures. This is a really ugly picture. This is a picture that's not really a picture. It is a collection of data in the infrared part of the spectrum, heat, basically. It's the heat signature of Mars collected by the Thermal Emission Spectrometer. It was one of 7 instruments on the Mars Global Surveyor. And the thing that that instrument was able to do was identify where different kinds of minerals were on the surface of Mars. This allowed geologists, and I hesitate to use that term in reference to Mars because, you know, geo is Earth and Mars isn't Earth. But if I say areologist, nobody knows what I'm talking about. Okay, a Mars geologist looking at this will be able to tell just from this data, from this instrument, where different minerals that are found on Earth are also found on Mars. Tons of data like this was collected through this mission, which was active up until just after the year 2000. It's been about 4 or 5 years collecting data. And one of the most insightful things it detected was the signature of a chemical called hematite. You've probably never heard of hematite unless you really like jewelry, because hematite is a really cool little stone that can be used to make certain kinds of jewels. But the detection of hematite on Mars, not the jewel kind of the more boring mineral kind, was really interesting because on Earth, there's only 2 ways to make hematite. You can make it in a lab, or it forms naturally in the body of liquid water. Either way, that's exciting. We're pretty sure the hematite on Mars didn't come from a Martian lab. Probably it came from Martian water. And in fact, the data that was collected by this 1990s mission was used to find a spot where there was a whole bunch of hematite all in one spot, and it was used to direct one of the next landers on Mars to a landing spot. What you see in the inset picture there, that's Meridiani Planum. That is a spot on Mars that has the highest concentration of hematite anywhere on the planet. And that little ellipse in the middle, that is where the Opportunity rover landed in 2004. Well, nowadays, the exploration of Mars is a very dynamic endeavor. We get spectacular pictures back from it. We have multiple spacecraft operational on the surface. We also have spacecraft that are sending back data that supports the operations of other missions. We've got a terrific camera in orbit on the Mars Reconnaissance Orbiter. It usually takes pictures of Mars. It can take pictures of other spacecraft. There's a great picture of the 2012 rover, the Curiosity rover, landing on Mars on the left-hand side. I still can't believe they got a picture of a robot under a parachute descending towards the surface of Mars 9 years ago. That was awesome. We are able to monitor the weather on Mars. There's a rover looking over its shoulder at the upper right. We can see a dust devil in the distance. We have spacecraft on the surface, like, again, a Curiosity rover, which is down at the lower right, able to send data up to orbiting spacecraft that then relayed it to Earth. So they can send a lot more information back to Earth than if they had to transmit directly back to JPL. And one of the coolest things that comes from having so many spacecraft at Mars for so long, we're able to see things that are changing on a day-to-day, week-to-week, year-to-year basis. The picture at the lower left, that's a picture of channels incised on the rim of a crater in the mid-northern latitudes on Mars. These are significant, not just because they're channels, well, maybe they were carved by a liquid, maybe something like water. And they're significant because the orbiting robot that took the pictures of these channels took another picture of the same crater 2 years earlier, and the channels weren't there. What does that tell a Martian geologist? That tells a Martian geologist whatever carved those channels just happened. It's not something from 1 billion years ago, 1 million years ago, even 1,000 years ago. That could have been yesterday. And again, this is very exciting for us in terms of understanding Mars as a dynamic, active planet. Well, what's happening this week? There are actually 3 missions that have arrived at Mars over the last week and a half or so. There's a mission from the United Arab Emirates that went into orbit last week. That was HOPE. We have the Chinese mission. Ooh. Oh, here it is. Taiwan 1, yes. The Chinese were very successful with Taiwan 1 going into orbit around Mars last week. A few weeks hence, they're going to attempt to land a spacecraft on the surface, and that'll be intriguing to see how that goes. They're picking an entirely different landing site for their mission, which also includes a rover. Our next spacecraft landing on the surface is Perseverance. It's the rover that we see at the upper right. It is derived from Curiosity, which was the rover that was launched in 2012 and which has been rolling around on Mars ever since. It's a little bit bigger. They redesigned the wheels because there were some issues with the wheels. It's got two things on it that the earlier rover did not. So it looks very, very similar, but it's got two major upgrades. First, and this is exciting, it has the ability to collect samples on Mars and put them in canisters, which can be collected by a later mission and returned to Earth. That's something scientists are very interested in doing. It's going to be a process. They're going to have to be at least 2 more big robotic missions in order to collect and return these samples. But by having Perseverance collect these samples on the surface of Mars in the location where it's landing, that's the first step towards getting things back to Earth. Second, and this is why it's exciting for us here at the Hiller Aviation Museum, above and beyond my personal interest in Mars, it's got a helicopter on it. The Mars Helicopter Scout was originally a proof of concept initiative at the Jet Propulsion Laboratory down in Pasadena, just to see if it was possible to design a drone helicopter to fly on Mars. The results were quite favorable, and they approached NASA about 6 years ago. Hey, you know, this thing isn't going to be very heavy. Can we hitch along with the next rover and experiment with it and see if we can get the helicopter to fly? And after a careful risk analysis of it, just to make sure it wasn't going to cause any problems for the main mission, NASA said, sure, let's do it. So right now, approaching Mars is a helicopter, which I'll talk about momentarily. And that's another thing that makes this mission just a little bit different. Now, the destination of this mission, where it's going to be tomorrow, whether it's intact or whether it's in pieces, we're not sure yet. But where it's going to land or fall tomorrow is the crater that's in the background here, Jezero Crater. And once again, this landing site has been chosen specifically based on orbital data that's been collected by other spacecraft. If you look carefully, you'll see at the upper, ooh, do I still have, oh, hey, I got a little arrow here. If you look over here on the western end, you notice that the rim of the crater has actually been breached right here in this spot. And it looks like there's almost something like a river coming through here. And for those of you who are into rivers, this kind of looks like a, whoops, I lost my arrow, there we go. This almost looks like a delta, like you would see at the end of the Mississippi River or the Nile River or a big river on Earth. All right. There's actually another one of these features over here on the other side, but the landing site that's been selected is this area right in here, because the evidence that's been collected from orbit suggests that there was water filling this crater, kind of like a Martian version of Crater Lake, for a really long time in the past, and that new water was continually being brought in. It wasn't one of these things like where Pathfinder landed, where there was a flood that lasted a few weeks or maybe a couple of months and then the water was gone. This is a place where water was on the surface for a long time, which makes it really intriguing to explore. This is JPL's commissioned artwork of what they think Jezero looked like in the past. Again, it looks a lot like Crater Lake. It's just redder and drier out around it. It did have 2 different drainages, and the idea that we can study sedimentary features that come from water in a place on Mars that's probably been dry for hundreds of millions, if not a billion years. That's, again, very compelling to this whole business of following the water to understand the history of water on Mars, to understand the potential for whether or not life might have been there in the past. All right, I've got a picture here that's kind of technical, but what I'm going to do is see if Jeff Bass can take over for a moment and share with us a 59-second video that will hopefully be able to show us what the Perseverance rover will be doing tomorrow, our time, between about 12:45 p.m. and about 12:55 p.m. Jeff, you want to give it a try?
I'll give it a shot.
All right, that is the quick version there. If you want to see the version without the little stops and goes, you can go and do a search on YouTube for Perseverance rover trailer. JPL called it its trailer out there, and it'll pop up pretty easy. That little video is 59 seconds long. The actual process by which that rover is going to reach the surface of Mars only takes 7 minutes. The NASA geeks like to call it their 7 minutes of terror. It's actually longer than 7 minutes of terror because Mars is so far away, the radio signal from Mars takes a lot longer than 7 minutes to get here. So when the signal arrives at the control center in JPL that, oh, the spacecraft is at the top of the atmosphere, the 7 minutes is starting, the 7 minutes is already over. The rover is either landed or it's crashed. It's just a radio signal, or lack thereof, hasn't made it back from Mars to Earth yet. So there's nothing the controllers can do during that process except sit and watch and let us know what happened. So that'll be happening tomorrow. We do recommend, if you want to join that, the best place to go is probably NASA's YouTube channel. We have a link to it in the e-blast we sent out earlier this week. It's also very easy to find. And again, they're going to start at 11:15 a.m. tomorrow, our time, Pacific time. The landing itself is supposed to happen 12:55, and that's what time we will receive the radio signal from the surface. The last thing we're gonna, oops, let's make sure let's try looking in here. Okay, there we go. And then the last thing I want to briefly go over is this business about the Ingenuity Mars helicopter. It is a very small helicopter. It is the very first powered aircraft that hopefully will have an opportunity to attempt to fly on Mars. It is not, however, the first aircraft that will fly at another planet. That actually, hats off to the Soviets. I told you they got sick of trying to go to Mars and failing over and over again. They specialized on Venus. And one of the most unique missions they sent to Venus was in 1985. They built 2 spacecraft that traveled to Venus and then went from Venus on to Comet Halley. It was Vega 1 and Vega 2. When they passed by Venus, they dropped off a couple of capsules that entered the Venusian atmosphere and deployed balloons. Balloons are considered by the FAA to be one of the different types of aircraft that you can actually get a balloon license instead of an airplane license, or a balloon certificate. Actually, it'd be a little more accurate there. There was no balloonist aboard the Vega 1 balloon or the Vega 2 balloon. They were robotic balloons, but they did float in the Venusian atmosphere for about 48 hours, and they returned data, no pictures, but they returned data on wind speed, temperature, pressure, direction they were going, and it's a fabulous mission. They were not powered, however. The Mars helicopter is powered, and if you look at that little picture, there's a little square panel. Actually, it's rectangular on the top of the rotor mass. That's a tiny solar panel. A solar panel doesn't generate enough electricity to fly the helicopter on an ongoing basis. What it will do is the helicopter will sit on the Martian surface. It will collect solar energy all day. It will charge a battery. And that battery will then have sufficient power once per day to fly this helicopter for about 90 seconds. The farthest it can possibly get is about 1,000 feet. Those numbers are actually not that different from what Wilbur and Orville Wright were able to achieve with the Wright Flyer. They, on their best flight on December 17th, 1903, they were able to go about 1,000 feet. They were able to fly for about a minute. So it's very close to what the Wright brothers were able to do. Now, obviously, you're not going to have a Wright brother lying down on this thing as it flies. You'd crush it. It's only about 4 feet across at the rotors. It only weighs about 4 pounds. It's not very big. But one of the things that I really find inspiring is the way the rotor system works. If you'll take a look, it doesn't really look like a traditional helicopter. It doesn't even really look like a traditional drone. We're used to the quad rotor format for drones. There's a lot of reasons for that. That was going to be a little bit difficult to engineer in a format that was going to work at Mars. What instead the JPL folks settled on is the design you see here with a single rotor shaft with 2 different rotors. Those rotors turn in opposite directions. That's called coaxial rotors. It's not a new idea. It's actually been around since early in aviation history. As a matter of fact, the museum's founder, Stan Hiller Jr., used that design in his very first helicopter, the XH-44. The original XH-44 is on display now at Udvar Hazy Center in the Smithsonian, but the yellow thing behind me is a replica built by Hiller Aviation Museum volunteers a few years ago, and it will demonstrate for us this whole business of coaxial rotors. Hopefully see how this works. Even more hopefully you'll still hear me. Now, the advantage that Hiller was looking for, having rotors that turn in opposite directions, we have a tiny little electric motor that's causing this motion. The real Hiller XH44, it'd turn at several hundred RPM, actually a couple thousand RPM. So they'd be whirling around like conventional helicopter blades. But this gives you the idea. They turn in opposite directions. And because of that, there is no need for an anti-torque rotor. Most helicopters, we have many that are here, or we've got a Hiller H12 overhead with a traditional design. They have that tail rotor. That's a very heavy structure. It's an additional mechanical complexity, and it's there to prevent a single rotor turning around and around from imparting torque to the helicopter and making it spin around and around. That's a big problem. You don't want that. The idea that Hiller had was to save the weight and mechanically wasted energy of operating a tail rotor by using two main rotors turning in opposite directions on the main shaft. The torque from each rotor cancels the other rotor out and allows the helicopter to be smaller, lighter, and more mechanically efficient. And for all of those purposes, the design works. Of course, there's a reason you don't see helicopters like this very often here on Earth. And the reason for that is, yeah, they are very efficient and they're very light, but unfortunately, they are hard to do anything other than hover in. It's much more difficult to get a helicopter with coaxial rotors like this to fly forward and backward, left and right. You can do it, do it more slowly. You do it just a little bit more slowly. However, on Mars, the goal is to have the lightest and most efficient possible helicopter. Those are advantages that you can get from this kind of system. And you don't want it to fly too far. You just want it to be able to fly within an area that the rover can watch. The whole idea with this helicopter is to test the technology. We want it to fly just in front of the rover, not right in front of it, a little bit farther out, but within view of the rover's camera so that it can collect data. There is a camera on the helicopter as well, so we'll get to see its bird's eye view if it flies successfully over the Martian surface. But this is the reason that JPL has gone this route and is bringing back what in many ways is an older technology. All right. So we're in the home stretch here. And then where I'm going to end is the places this technology can take us. Again, this helicopter is not the primary focus of the mission. This helicopter is an add-on. It's a technology demonstration. It's not going to fly tomorrow. It's designed to fly a month or two after Mars landing if everything goes well, and it'll fly maybe 5 times over the course of a month. If it's super successful, it might fly more than that. Most likely, they'll try something a little bit more adventurous and it'll fail and it'll break and there'll be no opportunity to repair it. But it's going to collect data. That data might allow future helicopters to be used as scouts. That's the original goal for this helicopter, is to be a scout and to let a rover team that's driving a future spacecraft on the surface of Mars see where it's going. But Mars isn't the only place where this technology is applicable. There's another mission that's actually been approved. It's funded. It's in development right now. It's called Dragonfly, and it is planning to build this helicopter that you see right here. It's not for flight at Mars or even Venus. It's intended to fly at Titan. Titan is a moon of Saturn. It's a very large moon. It's about the size of planet Mercury and has a thick atmosphere. And the atmosphere and low gravity present in Titan make it very suitable for helicopter flight. In some ways, it's easier to fly a helicopter on Titan than it is on Mars. You just have to use nuclear power instead of solar power to charge up the battery. So this is actually a 12 rotor drone. That's for redundancy, so some of the motors can fail and it'll still be able to fly. And it's intended to launch in 2027, and it's got a long way to go to get out to Saturn. But it's very exciting to see vertical flight and helicopters having applications beyond what we see here on Earth and even out at Mars. All right? All right, folks, thank you very much for joining us. Again, if you're interested in watching the Perseverance rover landing, it's going to be cast by NASA and JPL tomorrow. The YouTube channel that NASA operates is probably the best place to go. If you have NASA TV available on your television, they have a streaming channel for it. Any of those would be perfectly suitable ways to get in there. And again, thank you for joining us tonight. Jeff, I'll turn it over to you if you've got any questions that you want to pop out here. I'll take any ones that you read out to me.
Sure. Thank you, John. Well done. Interesting. For those of you who do have questions, and there are a couple, go ahead and type them into the chat. We are reaching the top of the hour, so if you have to jump off the Hill or Hangar talk, that's fine too. We're going to hang out here for a couple of extra minutes, maybe go over a little bit answering questions, but it's okay if you decide you need to jump off, no worries. Before I get to the questions, let me just double check and remind everybody again that the live streaming for tomorrow's event on NASA TV, you can either go to YouTube to the NASA YouTube channel, just type NASA YouTube channel in the YouTube search window and you'll find it. Space.com also is going to cover it. They have a link also to NASA TV as well. And as John mentioned, the coverage starts at 11:15 Pacific time tomorrow. The landing happens at 12:55, just before 1 o'clock Pacific time. So anyway, that's something to keep in mind. Let's take a look at the questions. Okay. From Gigi, can you compare the capabilities of the UAE, the United Arab Emirates, and Chinese Mars robots to Perseverance? What are the differences in what their kind of mission objectives are that you're familiar with?
All right, well, I will say right off the bat, I'm not that familiar with either of those missions compared to Perseverance. On the other hand, a week ago, I wasn't that familiar with Perseverance's role either. The UAE mission is called HOPE. It is the first mission that that country has put out into interplanetary space. It's a very exciting technical achievement. The spacecraft was actually constructed by Lockheed Martin Astronautics in Colorado under the direction of UAE engineers and scientists. It was then launched by the Japanese Space Agency from their facility on Tanegashima Island. So you had spacecraft from all over the world being launched to Mars in the last Mars launch opportunity. The spacecraft has imaging science and also is designed to collect remote sensing data from orbit. So it is, again, one of these orbiters, sort of like the Mars Global Surveyor, and it's designed to collect data from orbit for a long time. The Mars mission that the Chinese have is kind of intriguing. It's very reminiscent in some ways of the Viking mission that was operated by the United States back in the late 1970s. The biggest difference is the spacecraft. There's only one of them. There are two Vikings. There's only one Tianwen spacecraft, Tianwen-1. It's in orbit of Mars right now. The similarity is that the entire spacecraft is orbiting Mars and the lander will separately detach at a later point, re-enter Mars's atmosphere and land. The advantage that has is whereas Perseverance is going straight from Earth directly to the surface of Mars without slowing down into orbit, it's going to hit the atmosphere going very quickly, about 11 miles per second. Whereas if you enter from Mars orbit, when you reach the top of Mars's atmosphere, it's more like 7 miles per second. So it's not going to hit the atmosphere going as fast. It makes it a little bit easier to land. It is carrying a rover. The biggest difference in the rover delivery system, you might have noticed in the video that we ran, there's this crazy thing called a sky crane that JPL developed, and it worked successfully 8 years ago. So there is demonstrated proof that this can be done. The rocket stage hovers about 30 feet above the ground, and then it lowers the rover directly onto its wheels onto the surface with a series of tethers. Then the tethers detach and the rocket stage flies away someplace and crashes in the distance. The reason JPL developed that is so the rover would land straight down on its wheels. The Chinese design is in some ways a hybrid between the Viking landing system where the rocket stage goes directly down onto the ground and what we did for the Pathfinder mission back in the late 1990s, wherein the rover is attached to the lander and then it has to use ramps to get off the spacecraft. Now, the Tianwen rover is substantially larger than Sojourner, and unlike Sojourner, it will have a direct link to the Chinese mission control on Earth. It's not as big as, say, Curiosity was, or it's not as big, it's definitely not as big as Perseverance is. Those are very large rovers, about the size of a small SUV. They're more comparable in size to the Mars exploration rover Spirit and Opportunity that the United States landed on Mars about 15 years ago, back in 2004, 2005. Also, like those older rovers, it's solar powered. So solar power is a lot easier to build a rover around. But once you're on the surface, one of the reasons the United States went to nuclear power for the last 2 missions, not a reactor per se, but basically a nuclear battery that takes decaying plutonium and turns it into heat from it into electricity. Uh, Solar power, the solar panels get dusty. There's a lot of dust on Mars. I mean, global dust storm, 1971. Hasn't been the last time. It happens all the time. And Spirit and Opportunity perpetually had issues with dust getting on their solar panels, and they had to hope that a dust devil would come by and clean them off again. That would happen every once in a while. So it is similar in capability. The Tianwen rover is similar in capability to Spirit or Opportunity. The instrumentation, I'm not certain how efficient the instrumentation is compared to those 2 missions. The landing sequence is in some ways more similar to a combination of Viking and Pathfinder. Hopefully that kind of gives you an idea of the mission profile. It will be intriguing to see how that plays out over the next couple of months. It's for both the UAE and for China. It's very impressive they were able to successfully put these spacecraft in orbit around Mars on the first try. That's something the Soviet Union couldn't do. That's something the United States couldn't do.
Okay, good. We had a question in there, but you actually addressed it, and that was how big is Perseverance? And you mentioned that it's roughly the size of an SUV. So this is a big vehicle. So you definitely think of it in those terms. Couple of other questions, and again, if you need to jump off because we're after our 8 o'clock stop time, you can go ahead and do that. We're going to go through these questions. One of the questions that was sent to me was, what extent, if any, have modern drones and gyroplanes and rotorcraft, that's a big selection of vehicle types, helped in the research and development for Ingenuity? I mean, obviously the biggest factor is the thinness of the Martian atmosphere. There's not a lot of air to beat into with those rotors. It's got to be rotating pretty quickly, I would think.
Yeah, if I can hop on there, the Ingenuity helicopter, the one that's actually on the way to Mars right now, was tested in a chamber at the Jet Propulsion Laboratory. I had an opportunity to see it when I was touring JPL a couple of years ago. They had just finished the test, so I saw the chamber right after they took the helicopter out of it. That would have been even more cool. But the system they used was quite ingenious. They placed the helicopter in a giant vacuum chamber, not as big as this gallery. It didn't fly it that far. It was as big as maybe a tenth of this gallery. They took most, but not all of the air out of it. And then here's the tricky part. They had to attach it with a tether to the ceiling, and the tether had to take up about 67% of the weight of the helicopter to simulate Martian gravity. So in this environment, they were at Martian air pressure. They were at Martian air composition. So instead of the oxygen, nitrogen we have on Earth, it was carbon dioxide, which is the Martian atmosphere, and at Martian gravity, and it was able to fly successfully. And Jeff, as you mentioned, the RPM reached by those rotors is very high. These are big rotors. The rotors are very similar to the rotors that would be used for a RC helicopter here on Earth. It's carbon fiber, very similar. Any RC helicopter pilot would probably find them very familiar looking. Compared to a regular RC helicopter, they're bigger. Again, a little bit more than a meter in diameter, so pretty large. And there are 2 sets, counter-rotating. They turn really, really fast. And one of the most challenging parts of designing this helicopter, in my understanding, is the battery system and the energy management system for the solar panel to be able to charge the power system, and then for the power system to turn around and very, very quickly power the engine to allow a 60 to 90-second flight.
Okay, fascinating. We're going to finish up with one last question here, and it's a good one. It's a question about Perseverance entering the Martian atmosphere. The Martian atmosphere is thin. How is it able to slow down from 12,000 kilometers or miles per hour to approximately 900 miles per hour if the air is so thin? And is there a sonic boom when it passes through the sound barrier?
That is an excellent question. Mars is an incredible pain to land on. Landing on the moon and landing on Earth are in some ways easier than landing on Mars. On the moon, there's no atmosphere whatsoever. You can take the ugliest possible spacecraft with no aerodynamic qualities whatsoever. You just need to have landing legs and a rocket motor that can slow it down. If you send that kind of robot to Mars, the atmospheric pressure as it enters at high speed is going to rip it apart. On Earth, there's a very thick atmosphere. If you enter Earth's atmosphere, you need excellent heat shielding, but Once you slow down to a certain point, a parachute will bring you down to a very reasonable speed that you can take almost all the way down to the surface. You can ride a parachute all the way to the surface if you land in the water, within just a few feet of the surface if you're landing on land, and then you just need a rocket to cushion the last few feet. That's the way the Russians recovered their Soyuz spacecraft. The spacecraft back in the Apollo era and modern SpaceX Falcon, things of that nature, they land into water to take care of that last little bit. Neither of those techniques will work on Mars. There's enough atmosphere that it will kill you if you don't pay attention to it, but there's not enough atmosphere for it to slow you down. And that's why over the past 20 years or so, JPL has gotten to be very creative with their landing systems. All Mars landers need a heat shield for the first part of the journey. So they arrive at Mars and they're going many miles per second. The heat shield prevents the frictional heating from entering the upper atmosphere at Mars from incinerating the spacecraft. It will slow down aerodynamically, much like an Apollo capsule or a Falcon X capsule or a Soyuz, and get down to a reasonable speed, something that's still supersonic, but a reasonable speed. And this is another difference. On Earth, if you're entering the atmosphere like this, you can get subsonic just re-entering the atmosphere using your heat shield and slowing down. That doesn't happen on Mars. The atmosphere is not thick enough to bring you to subsonic speed. There is a sonic boom. There are actually 2 microphones on this spacecraft, but since they're aboard the spacecraft, they will not have an opportunity to detect a sonic boom. If you had a microphone on the surface in the right place, it probably would detect the sonic boom, even with the thinness of the atmosphere. That would still be a reasonable expectation. But instead, a parachute has to deploy at supersonic speeds. Our local NASA Ames Research Center has been used extensively by JPL for research into the aerodynamics of supersonic parachutes, because you just don't deploy parachutes at supersonic speeds on Earth. There's no reason to do that. It's just not necessary. If you're going supersonic, you slow down first. If you're a pilot on a supersonic airplane, you eject, and then your body slows down to subsonic speeds, and then your parachute opens up. Mars is a different deal. If you wait until you reach a subsonic speed, you're going to be on the ground already. You're going to hit the ground at high speed. So the parachute has to open at supersonic speeds. That's great. It doesn't slow you down enough to be able to safely land. It's that last little bit that you need to do something else. The Viking landers used rockets to propel all the way down to the surface using rockets. It's kind of like the Apollo landing on the moon sort of business. The Pathfinder, Opportunity, Spirit spacecraft, they used an airbag system. The spacecraft would literally be dropped from a short height after doing most of their slowing down with the heat shield and with the parachute, and then they would bounce. The system that's been used for the Curiosity rover, and that is going to attempt to be used tomorrow for the Perseverance rover, it's kind of a hybrid. There are no airbags, but the rocket stage will fire kind of like the Viking spacecraft did, slow the spacecraft down after the parachute is jettisoned, and then instead of using airbags or instead of propulsively going all the way down to the surface, you have this skyhook thing where the tethers lower the rover so it's sitting on its wheels as soon as it reaches the surface. But yeah, that whole business with Mars, there's a JPL engineer who explains it in a narrative video as being there's just enough atmosphere that you have to deal with it, but there's not enough atmosphere to let you safely land. So you have to do something creative in order to make it all happen. And that's the whole entry, descent, and landing sequence.
Excellent. Thank you, John, for that incredibly interesting talk. It's going to be fascinating to watch what happens tomorrow during the landing phase. Again, it starts at 11:15, the broadcast, and then 12:55 Pacific time is when the landing is supposed to take place. Thank you, John. And if you enjoyed his talk, by all means, show your appreciation by using the reaction features at the bottom of your Zoom screen to give him a hand clap or a thumbs up, and getting us all prepped for tomorrow's exciting arrival of the Perseverance lander at Mars. There probably were a couple of extra questions left. We do have to wrap it up, but what I'm going to do is I will collect all those questions in the chat and give them to John, and he'll be able to reply to you directly for anyone who still had questions for John after the talk. So in the meantime, I would like to thank you all for coming tonight. Don't forget to join us 2 weeks from now when we have bush flying in Alaska with Darren Pleasance on March 3rd. And in the meantime, stay safe. We're looking forward to reopening soon at the Hiller Aviation Museum, and enjoy the landing of Perseverance on the planet Mars tomorrow. Good night, everybody.
Good night, folks.
I figured out, I know why Mars